Inclined plane problems. I'm going to use forces to solve this inclined plane problem. So, fine, for inclined plane problems, it's best to start off as you read the question, draw what's happening. So I'm going to draw what's happening. I'll draw an incline. Just a simple diagram of the object on the incline, frictionless surface, 20.0 degrees, and then examine the forces. The force of the gravity, of course, can only pull straight down. And the normal force is the force pushing directly away from a surface, like so. On this one, we also have friction. Now, friction is preventing it from sliding down. It's keeping it stationary. Friction always opposes motion. So that would be up the incline, like so. There's our three forces for our free body diagram. Always start off force questions by drawing a free body diagram. Next, well, I find for pretty well any inclined plane question, it's good to examine the components of the force to the gravity. So force to the gravity is this arrow going down, but I'm just going to take that arrow and sort of swing it up over here and point it upwards. And why am I doing this? Because then opposite the angle, geometrically, the parallel component adjacent to the angle will always be the perpendicular component. Now, if I run across an inclined plane problem, I'm not too sure what to do, this will always be part of the solution. And you will always need to be calculating that parallel component. And quite often you need this perpendicular component too. How do I calculate the parallel component? Well, it's opposite the angle, so I'm going to use sine. Sine of the angle is going to be opposite over hypotenuse, of course. Now, what is the hypotenuse? Well, it's force to the gravity. M times G, let's see, 10 kilograms on the mass. 9.81 is what we'll go for acceleration of gravity. Also 98.1 newtons. Great. So with this, I can calculate the parallel component. The parallel component is going to be F parallel equals force to the gravity times sine of theta. So that's going to be 98.1 newtons times sine of 20 degrees. Let's make sure we're in degree mode, of course. So 20 sine times 9.81 equals, and I've got a value for that, 33. Okay. I'll put a couple extra digits for now. I'll round off to proper sig digs at the end. Great. Now, do I need the perpendicular component? Sometimes yes, sometimes no. I find especially if there's a coefficient due to friction involved, you'll need it. Otherwise, quite often, you won't, okay? You won't. Realize, of course, it is going to be equal to the normal force. The normal force. When I come over here, I have three forces acting on this mass, but if I want to put in the components of gravity, I would put in this as being my perpendicular, right here, a perpendicular, that's a perpendicular symbol. And of course, parallel is trying to bring it down the incline, competing against force due to friction. That's important to realize that. This whole thing is stationary, I'm told. It's just sitting there. So friction must be counterbalancing that parallel component trying to drag it down. That's going to be an important part of the thing. So in other words, realizing since the net force is 0, it is stationary, I could say therefore the frictional force is equal to the parallel component, like so. That's what I'm going to deal with there. So the parallel component is 33.55. Oh, therefore the frictional force is also 33.55 newtons, like so. So I've answered the question. What is the value of the frictional force required? Value of the frictional force, the appropriate number of significant digits here. And it looks like we're dealing with two significant digits, 10 kilograms, along with 20 degrees. So 34 newtons is what we have. And we're done.